and paleoceanography. And today we will hear something about leaf waxes and CO2 reconstructions from leaf waxes from IODP sites. Yes, and I just got a notice here, I forgot to mention, we will record the talks, at least this first talk today, but we won't record the discussion afterwards. And the format of the series is that Masanobu will talk for about 20 minutes. Then you will have time for some direct questions and discussions. And then we will hand over to our second speaker, Tom Chalk. And after another 20 minutes, there will be another time for discussion. And then we will stop the seminar series at 3 p.m. Okay, by this, Masanobu, the floor is yours. I welcome you and I'm looking forward to your talk.
Yeah, Martin, thank you very much for your detailed introduction. So I will share my slide first, and this one.
Mm-hmm.
Laser pointer. Yeah.
Yeah, we can see it.
Yeah. So good afternoon. I'm Masanobu Yamamoto of Hokkaido University. So I'm very happy to be invited to this seminar and to have a chance to talk about our study. So this study was conducted in collaboration with Steve Clemens and Yonson Huang of Brown University. And my colleagues, Tomohisa Irino and Osamu Seki, and my student, Yuko Tsuchiya of Hokkaido University. And Ryota Oishi-san and Ayako Abe-san, they are attending this seminar of University of Tokyo. So we reconstructed the atmospheric CO2 concentrations based on leaf wax carbon isotopes in the Bay of Bengal. So as you know, the reconstruction of CO2 concentration is essential to understanding the history of Earth's climate. So ice core is a precious archive of the CO2 concentration. So this blue zigzag line indicates the ice core record showing glacial interglacial cycle. So I hear that you are now extending the continuous ice core records to all the direction. Hopefully, we'll see the results. And but at this moment, we have to use different archives and methods before 800,000 years ago. So we analyzed the long chain normal fatty acid carbon isotopes in sediments from a sediment core in the northern Bay of Bengal here. So this black one indicates our results, carbon isotopic composition here. And the blue one is the EPICA CO2 variation. So surprisingly, the variations are very, very similar to each other. So we made a plot, carbon isotopic composition and EPICA CO2 concentration. Then we found a good correlation between the two parameters. So if this relationship was true before 800,000 years ago, then we can estimate the atmospheric CO2 concentration based on leaf wax carbon isotopes in sediments. Long chain normal fatty acid is this compound. This is a leaf wax of the terrestrial higher plants. So there are C3 and C4 plants and with different carbon isotopic composition. So if we see the carbon isotopic composition, we can distinguish C3 and C4 plants. And also we can evaluate the relative abundance of the C3 and C4 vegetation. The sediments were delivered from the Mahanadi rivers and small coastal rivers in East India. So the isotopic composition should reflect the C3, C4 vegetation in these small river basins. So there are three major potential factors affecting the C3-C4 vegetation. So CO2 and the precipitation and the temperature. But our results indicate that the only CO2 was a major factors affecting the C3-C4 vegetation ratio. But why? So this was the major question of this study. So C3 plants fixes carbon from CO2 by photosynthesis using Rubisco enzyme. This enzyme fixes oxygen and loses carbon, by photorespiration. So if the CO2 concentration is low, photosynthesis is suppressed compared with the photorespiration. So photosynthesis is not efficient. So this is the reason why C3 plants have this advantage in low CO2 condition. So on the other hand, C4 plants convert CO2 to C4 diacid. This diacid can be transported to the bundled cis cell. Then regenerated CO2 is fixed by a Rubisco enzyme by photosynthesis. Oxygen cannot be transported to this cell. So the oxygen concentration is low, so photosynthesis is efficient. So this is the reason why C4 plants have advantage in low CO2 condition. So this theory and inference were proved by free air CO2 enrichment experiments. So these experiments were conducted in the 2000s intensively. So meta-analysis indicates that the production of C3 plants is more enhanced than C4 plants in a higher CO2 level. So how about the Indian vegetation? So Oishi-san, Abe-san, conducted the vegetation modeling. So this is a C3 vegetation coverage and the C4 vegetation coverage, and at the pre-industrial level and the LGM level. So when CO2 drops, C3 vegetation slightly decreased. On the other hand, C4 vegetation substantially increased. So C3, C4 vegetation, responded to CO2 change in the Mahanadi River basin. So right panel indicates the world distribution of C3 and C4 vegetation, green one and the red ones, and the black cross indicates the Mahanadi River basin. So at the pre-industrial level, Mahanadi River basin is covered by C3 vegetation. But at the LGM CO2 level, Mahanadi River basin was covered by C4 vegetation. The climate didn't change so much, but the area of the C4 plants expanded to wetter and cooler region. So in this way, the C3, C4 vegetation in the Mahanadi basin, responded to CO2 changes. So this is the result of the sensitivity test with decreasing CO2, C4 vegetation increased. And the precipitation didn't change so much, and this small change didn't affect the C4 vegetation. We also compared the carbon isotopic composition with temperature and precipitation proxy records at the study site. So black one indicates carbon isotopic composition, and the blue one is the sea surface temperature based on TEX 86. So you can see C3 plants were more abundant in interglacials when the temperature was higher. So this relationship is opposite what is expected physiologically. So we think that the temperature is not a major factor affecting the C3, C4 vegetation. Oh, sorry. And this green line indicates the delta O18 of sea surface water, ocean water. So this was calculated from the oxygen isotopic composition of planktic foraminifera by collection of global ice volume and temperature effects. So the correlation is not good. And also we can find that the leaf wax carbon isotopic composition preceded the seawater oxygen isotopes. So this means CO2 affected the precipitation. So precipitation didn't affect the leaf wax carbon isotopes. So both temperature and precipitation are not the major factors controlling the C3, C4 vegetation. So we also analyzed the PTME. So this compound is almost specific to Poaceae grass. So black one, sorry. And this LCNA is the long chain normal alkane. So this is the common biomarker of the higher plants. So this ratio is assumed to reflect the grass abundance. So black one is the grass abundance. And yellow one is the hydrogen isotopes, delta D of precipitated water. So this was calculated from the leaf wax delta D. So this is a proxy of the precipitation in tropical area. So this means the precipitation, affected the grass abundance. But this yellow one didn't affect the C3, C4 vegetation. And this is a plot of the C3, C4 vegetation and grass abundance. So the relationship was not good. So this means they are almost independent. So this map shows the areas where the C3, C4 vegetation is responding to CO2 changes, green one. So these green areas were distributed widely in the tropical areas, and the regions are characterized by hot and seasonally dry climates. This corresponds to savanna vegetation. So you can see the Bay of Bengal is located here, and our site is here. So it's surrounded by green colored areas. And also you can see the Northwest Africa here is one of the area, please remember. And recently, Omar et al. 2022 reported that the leaf wax carbon isotopic composition is consistent with the EPICA CO2. So this means West Africa is also a candidate for the CO2 reconstruction by our method. So we applied this approach to the two different sites, 46 and 45. So we found a very similar relationship between leaf wax carbon isotopes and EPICA CO2 concentration. And we can make the regression lines, linear one and the curved one. So both correlation of determination is almost the same. So we tentatively use the linear regression line for the calibration from the carbon isotopic composition to estimate the CO2 concentration. So this proxy works within the CO2 level between 151 to 325 parts per million at the study site. If we change the study site, then this range also changeable. And the calibration error is 12 parts per million, and the calibration is site-specific and will not be directly applicable to other sites. So if we change the site, we have to make a calibration. So this study, this method is applicable if precipitation and temperature stayed in a particular range. So this is a limitation of our approach. So the record is independent of the I-square CO2 record on chronology and the CO2 estimate. So the obtained CO2 concentration is called CO2 FA in this study. So we will see the results, our results. It's a green one and the black one. So this one. Blue one is the EPICA CO2. And the yellow one is the Alan Hills blue ice values. So green one and the black one show the very similar variation. And compared with the blue ice, so our reconstruction seems to be lower than the blue ice. But the majority of the blue ice values correspond to the interglacial ranges of our reconstruction. So this is a comparison with the basic oxygen isotopic composition. It's a stacked record LR04. So this is a proxy of the continental ice volume and bottom water temperature. So you can see a cyclicity change from the 41,000 year cycles to 100 year cycles across the mid-Pleistocene transition. So CO2 seems to be tightly coupled with ice volume variation on orbital time scale. And this shows the long-term trend, moving average. So the long-term trend are different. So oxygen isotopic composition gradually shifted in a positive direction. But this tendency cannot be seen in a CO2 record. So this means CO2 concentration was low even when the ice volume was small. So this is a question. And actually, this trend was not expected. And because this is the world ocean sea surface temperature change across the MPT. So in most areas, sea surface temperature show a cooling trend during the mid-Pleistocene MPT. So this is not consistent with our CO2 reconstruction. But the exception is the Indo-Pacific warm pole region. So this is the warmest region on the world. And in the IPWP, the temperature was unchanged across the MPT. So this is consistent with our CO2 record. So we compared with the Indo-Pacific warm pool sea surface temperature, the high resolution records, you see, and we can find the very good agreement between the CO2 and the IPWP sea surface temperatures. Because the IPWP is far from the continental ice, so we can assume that the temperature was affected by greenhouse gas forcing more straightforwardly. So this correspondence is, I think, reasonable. But we cannot explain why our record is not consistent with the sea surface temperature changes in other oceans. So this is a big question for us. So in contrast to oxygen isotopic composition, so the carbon isotopic composition of benthic foraminifera, in particular in the South Pacific Ocean, so we can find a very good agreement, both on the orbital time scale and long-term trend. So this carbon isotopic composition of South Pacific Ocean is a proxy of the deep ocean circulation, and also this ocean is the storage location of the carbon, in the glacial period. So this means this carbon isotopic composition shows the is reflecting the ocean carbon storage. So this good agreement suggests that the CO2 was tightly coupled with the ocean carbon storage in the Southern Ocean. And also we want to point that our CO2 record shows the amplitude modulation like this. Then interval is about 400,000 years. This corresponds to the long-term eccentricity cycle. So when the eccentricity was low, the variation of the CO2, this is the standard deviation, red one, was higher. The reason is not clear yet, but this is an interesting phenomenon. So spectral analysis indicated the eccentricity and obliquity cycles after the MPT. And before the MPT, obliquity and I guess this is a double obliquity were dominant. And they were coherent. And the phase analysis indicates there are shift of the relative phase across the MPT. Before the MPT, CO2 preceded oxygen isotopes. And after the MPT, the relationship was reversed. So the difference is significant. So this is a record. Sorry. This is a record, CO2, black one, and the blue one is the oxygen isotopes of the basic foraminifera. So you can see after the MPT, blue one, oxygen isotopes, ice volume preceded the CO2, but before the MPT, CO2 preceded the ice. And the similar phase shift was observed between deep ocean circulation and the CO2, carbon isotope composition of basic foraminifera, or we can find the phase shift. So this is a record. After the MPT, the deep ocean circulation preceded the CO2, but before the MPT, CO2 preceded the carbon isotope composition. So paleoceanographic studies indicated that the deep ocean circulation substantially changed across the MPT, and also there are another studies. And I think the deep ocean circulation should be involved in the process of the MPT. Yeah, so this is the summary slide. So we tried to characterize the CO2 changes variation before the MPT. So these are the characteristics of the CO2 changes. So some of them are the same as that was already reported based on the boron CO2 record. But a significant difference is the concentration. Boron shows a higher concentration than ours. So this is a question for us. And also our record shows the amplitude modulation and the phase shift across the MPT. Thank you for your attention.
Thank you very much. Thank you, Masanobu. Very interesting talk. I'm sure there are quite a lot of questions.